If we stall when driving a car, it can be a bit embarrassing, but essentially it's no issue. When we stall an aircraft, however, things can get a lot worse and it can lead to disaster quickly if things aren't resolved. Why is stalling an aircraft so much worse? Let's find out. Hi, I'm Grant and welcome to Class 8 in the Principles of Flight series. We've now sort of covered the basic fundamental concepts involved with aerodynamics that we need for flying an aircraft. And we will now move on to the real-world applications and how we actually use our knowledge when flying an aircraft. In this class, we're going to be looking at the cause and consequences of stalling. In aviation, a stall is where the boundary layer separates from the surface of the wing over the majority of the surface, and the wing gets to the point where it is no longer producing much lift and the drag is very large. The reason behind this is a combination of adverse pressure gradient caused by low kinetic energy, which is brought on in part by energy loss at the leading edge. So energy is lost at positive angles of attack because some of the air hits the bottom surface of the wing and has to deflect around the leading edge like this. The steeper the angle of attack, the sharper this angle in here that is the air has to deflect around, and that means that more energy is used getting around this corner and it takes away energy from the boundary layer. Separation of the airflow occurs where there is not enough kinetic energy to overcome the friction force imparted onto the lower layers of the boundary layer, and this adverse pressure gradient is formed. So as we increase our angle of attack, we're making this angle that we need to overcome steeper and steeper, and it takes more energy away from the airflow. And if there's less energy in the airflow, the point where friction force becomes more dominant happens sooner and sooner, and that leads to the separation occurring further forward with an increasing angle of attack. So this is what we're seeing here on the graph. We're increasing the angle of attack, and coefficient of lift is increasing with it due to that rapid acceleration air around the front edge. Eventually we reach our max, and after this point the airflow is deflected around this leading edge so much the angle is too severe that it uses up too much energy, and separation will occur, which makes the lift produced reduce a lot. And the steep angle to the airflow also means that this part of the wing in here creates a lot of form drag, and so the drag will increase and the lift decreases. This is why we stall. Stalling is only dependent on the angle of attack. So to get out of the stall, there's only one solution. We have to reduce our angle of attack. Different wing designs and choices have an effect over the way the wing will stall. As we saw in the class on wing design, the coefficient of lift distribution isn't equal along all parts of the wing. So it makes sense that the points of separation aren't necessarily equal, and early separation and stalling isn't necessarily equal as well. One of the good points to look at to start with is the effect of aspect ratio. So with high aspect ratios like gliders, we get less downwash, and that means that there's a larger amount of lift produced due to that reaction force being more vertical than it is horizontal. The lower level of downwash also means that our effective airflow and our effective angle of attack are less steep than aircraft with low aspect ratios. So this would be something like a glider. You know, you've got your effective airflow being quite shallow, and then something with a low aspect ratio, you get quite a steep effective airflow. So as we increase the total angle of our wing to these effective airflows, the high aspect ratio wing will start to hit lower and lower on this surface. These lines here are just projected up, and you can see at this angle the high aspect ratio hits further down. So you can imagine all these lines coming along here they've got to deflect around a lot more than the low aspect ratio, which comes in here. It's just got to deflect a tiny amount. So this means that there's more energy taken away in the high aspect ratio wing. So we can make an assumption here, and we can therefore say that the larger the effective angle of attack, this angle in here, then it means the lower total angle of attack will be needed for the wing to stall. So if we link the effective angle of attack to aspect ratio, we can therefore say that as aspect ratio goes up and our effective angle of attack goes up, that means that our stalling angle will go down. So high aspect ratio means you've got a low stall angle. So the downwash in a rectangular wing isn't even along the length of the wing. So therefore the effective angle of attack isn't equal along the length. This leads to different parts of the wings stalling at different angles of attack. With a rectangular wing, we know the most amount of downwash occurs at the wing tips and the least at the wing roots. And because of this steeper effective airflow, it means that our effective angle of attack is actually lower. If we compare that to the root, the effective angle of attack is quite large, which means that the root stalls before the tip does. The stall occurring first at the wing root is generally good because the root section tends to be right in front of the tail of an aircraft. This means that the turbulent boundary layer starts to separate and the separated air hits the tail and causes something known as buffeting, which is a harsh vibration that will warn the pilot of the approaching stall condition. It also means that the ailerons at the wingtips remain effective for longer. The ailerons are controls near the wingtips that will increase the lift in that specific section of wing out of balance with the other side, and that causes rotation. It's how we control the aircraft. It's going to be covered in future classes, but that's just what you need to know for now. Because of these factors, the ailerons remaining effective for longer, and this pre-warning of the stall, this buffeting that hits the tail, this means that rectangular wings are really good for training aircraft because it allows for a safer environment in terms of stall protection. When we looked at the wing design class, we saw that elliptical wing designs are good because it creates a constant amount of downwash until the very tip where it suddenly drops off. This means that the induced angle of attack is constant and the reaction force is angled backwards at a constant amount, which gives us this constant coefficient of lift. A constant induced angle of attack means our effective angle of attack is also constant. What this means in practice is that essentially the whole wing stalls at exactly the same time. This means that the buffeting on the tail is felt almost immediately before you stall, and the ailerons, generally located at the wing tips, will stop being effective at the same time as the rest of the wing. So when you stall with an elliptical wing, the whole thing stalls, there's very little warning and you have very little control. With a tapered wing, we have a fairly consistent amount of downwash along the length of the wing, with increased amounts at the tip and the root. This gives us a good approximation to the elliptical distribution pattern. The downwash is lowest in the middle section of the wing. This means that our middle section of the wing stalls first. This in practice isn't very good because it means that the tail will generally be out of the stalling air, which means there's no buffet to give the pilots a warning of the stall. It is better than the elliptical design, however, because the ailerons remain effective up until later on after the middle part of the wing stalls. We saw the lift distribution pattern for tapered swept-back wings to look like this. The lowest induced angle of attack was at the wing tip, which caused this high coefficient of lift. The low induced angle of attack means that the effective angle of attack is actually largest at this point though. This means that the wing tip will stall first with tapered swept-back designs. With this design, there's also no natural buffet on the tail, and the ailerons quickly become ineffective. On a swept-back wing, the center of pressure also moves forward overall. This is because the wing tips are stalled and not producing sufficient lift, and they're located all the way back here when compared to the rest of the wing. So your average position, if this section of the wing is not working, generally moves forward. A center of pressure which moves forward will reduce the nose down moment caused by this center of pressure. If you've watched the series on mass and balance, you should know that the aircraft rotates around the C of G, and the center of pressure is behind it like this. If we move the center of pressure forward, that means that we reduce the balance arm of this center of pressure, and it means that the tail plane will then be out of balance and cause this upward nose up rotation. This nose up rotation obviously doesn't add to our problem. It means that more and more of the swept back wing stalls and the center of pressure continues to move forward and forward and forward. So the tail plane, instead of having to act down, has to reduce this strength, and eventually start operating the other way to give us a bit of up force as well to counterbalance this change in center of pressure movement. If this condition gets really bad, something called a deep stall can happen. The deep stall is caused primarily by this forward moving motion of the center of pressure, and it can get to the point where the tail can no longer overcome this nose up motion caused by this forward moving center of pressure. This leads to this runaway pitching up condition that we talked about. On aircraft with high tails, or T-tails as they're sometimes called, the deep stall can become even worse as the aircraft starts to lose altitude. It basically means that the separating airflow off of the wing completely covers the tail of the aircraft, and it means that the tail of the aircraft is trying to operate in turbulent air and it becomes ineffective. So wingtip stalls are generally bad. So how do we solve this problem? Designers use a few methods, and we're going to take a look at some now. So to counteract this wingtip stall, the designers try and restrict span-wise flow and also vary the shape of the wing and the incidence angle in much the same way as it is done for lift generation that we saw in that class. So by restricting the span-wise flow, you keep more energy in the boundary layer because more of it will be moving in the direction, leading edge to trailing edge rather than from root to tip. This means that the speed of the boundary layer at the wingtip can be increased, and more energy and higher speeds mean that the separation point occurs later. So to restrict this span-wise flow, you can use a physical barrier which will just actually physically stop any air from flowing either way. This is just called a wing fence, or you can use something called a vortilon. A vortilon basically disturbs the air and creates a vortex, which again has the same effect, and it doesn't allow air to actually flow. By modifying the angle of incidence, or washing out the wing, we can artificially lower the effective angle of attack and increase the angle of attack for stall. And also by modifying the shape in terms of the camber of the wing, we can adjust the local coefficient of lift versus alpha graph, and we can therefore change the point at which stall occurs. By rounding off this leading edge, we can also make the angle of deflection a lot smoother and keep more energy in that boundary layer. So we just talked about how wing designs will influence the stalling angle of attack, but there are a few more factors that will influence the stall based on the conditions that we experience when we're actually flying. So something important before we move on is to make a connection between the stalling angle of attack and the speed. So we know that lift will increase with a higher speed or a higher coefficient of lift. So our max CL is experienced just before the aircraft stalls and loses lift. For a fixed weight of aircraft, as we slow down, as this speed here reduces, we have to increase our coefficient of lift. If we go beyond our CL max though, the wing will stall. So this means that there is a minimum speed that we can go, because if we exceed it, our coefficient of lift will have to come from somewhere, and we'll keep increasing our angle of attack and we will stall. So for any aircraft, the coefficient of lift that comes from our angle of attack is also related to a speed at which we must travel, because if we go below that speed, we don't have the coefficient of lift to maintain the correct amount of lift to keep us in the air. So let's talk about wing loading. Wing loading is basically the weight of the aircraft divided by the area of the wing. And for an aircraft to be balanced, lift equals a half rho v squared SCL, but that also has to equal the weight. If it doesn't equal the weight, we're going to be either climbing or descending. A lightweight aircraft will have to produce less lift than a heavy aircraft of the same design. We said before that an airfoil will stall at a fixed angle of attack based on its design. So if we increase our weight and we have to increase our lift, we can't change our CL max. We can't really change the area because that's fixed by our wing design. But if we weigh more, there's one solution. That means we've got to increase our speed. So as our weight goes up, our lift also has to go up, and these factors can't be changed unless we use flaps or something like that. But if we're ignoring that for now, it means our speed has to increase. So if we're flying really slow at our CL max, our speed when we are heavier has to be larger to maintain the lift, whereas if we were lightweight, we wouldn't have to travel as fast with that same CL max value. This basically means that our stalling speed, our VS, will go up as our weight goes up, because we need more lift to counteract this weight. The ratio at which these stall speed changes occur is done according to the square of the speed. If we look only at the speed element, we can say that our weight must vary according to v squared, or our speed varies according to the square root of the weight. Then we use a ratio method to determine the stall speed changes according to the weight, and it's very simply our stall speed new over our stall speed old equals the square root of our weight new over our weight old. In the class on lift generation, we saw how extending flaps increases the overall camber of the wing. This increases our value for CL max. So then if we put the higher value into our equation for lift, if we want to maintain the same lift levels and we increase our CL max, it means we can get away with flying at a slower speed. So with flaps out, our stall speed will decrease. We don't need as much of our lift to come from the speed because we've got more of it from our increased CL max. This is why you extend flaps for landing. It allows us to decelerate and still create the correct amount of lift and not stall as we slow down. The change in stall speeds caused by flaps and slats extension is also related to v squared, as you can see here. From this relationship, we can derive a ratio formula like we did for weight, but it is slightly different because we're on the same side of the lift equation. Basically, we can get a formula which is like this. Our stall speed of flaps over our stall speed when we're clean is equal to square root of our CL max clean over CL max flaps. So it's much the same way, except because we're on the same side of the equation, we reverse it. And the CL max value is just reflective of having the flaps out and our graph overall shifting up. So when we extend the landing gear, it will also influence the stall speed. This is because as you extend the landing gear, you effectively increase the drag underneath the aircraft, underneath the CFG like this. This means that it will cause a rotation like this, a nose down pitching moment. To overcome this nose down pitching moment, we increase the downforce here at the tail. By increasing the downforce, we're adding to the weight of the aircraft. So our new lift value has to equal half rho v squared SCL, which equals the weight plus the downforce. If we need more lift and we can't change our coefficient of lift, it means that our stall speed, or our speed in general, has to go up. So we can't fly as slow with the gear down as we can with the gear up. So gear down, stall speed up. Thrust can influence our stall speed as well. So on a propeller aircraft, the air behind the propeller accelerates over the wing. This means that there is more energy in that boundary layer and it pushes the separation point to a higher angle of attack. On a jet aircraft, at high angles of attack, the thrust has an upward component as well as a horizontal component. This takes away from the amount of lift that is required, because this takes away from our weight, and this means that a slower speed can be achieved if you have high thrust than if you have low thrust before you stall. In practice that is a bit weird though, because if you've got more thrust on, generally you're not going to be flying slow, you're going to be speeding up. The influence of center of gravity of position is important, because a forward center of gravity means that our center of pressure has a longer balance arm than if it was further back here, for instance. This means that the aircraft with the forward CFG produces a larger nose down rotation. And to counteract it, we need to have a larger amount of downforce at the tail here. This downforce is added to our total weight of the aircraft, similarly when we looked at the landing gear situation. So our lift equals half rho v squared SCL, which also has to equal the weight plus the downforce. So if the downforce goes up, that means that our lift has to go up, and it means that if we don't change our configuration, our speed has to go up. So forward CFG makes our stall speed increase. We can't fly as slow because we need to have more lift to counteract this downforce that gets added on. Altitude influences are pretty straightforward. At high altitudes, our density is lower, so if we don't change anything about the wing, we have to increase the speed. So as altitude increases, our stall speed also has to increase because our density reduces. As we maneuver our way around the world using pitching and turning of the aircraft, we're essentially rotating around an imaginary corner every time we do one of these maneuvers. By rotating around this imaginary corner, we also add a centrifugal force to the aircraft which needs to be overcome. When you're in a car and you go around a corner quickly, you're forced to the opposite side of the car because you're not equalizing the centrifugal force. Car doesn't skid off the road because it does equalize this centrifugal force. It does this through the friction force in the tires of the car. In an aircraft, we experience these centrifugal forces when maneuvering the aircraft, and to overcome them, we have to increase our force into the turn. So when we're turning, our lift equals half rho v squared SCL plus the weight, which equals the weight, plus the centrifugal force. The amount that we need to increase this lift force is dependent on something called the load factor. Basically, it uses trigonometry and the centrifugal force to find out what increase in lift we will need. So we look at the angle of the bank. It depends on the bank angle. and we use cosine because it gives us the adjacent over the hypotenuse. We get the hypotenuse, which is the central force, and the adjacent will be our weight. And then we rearrange, and we're looking for the factor of increase. We're not bothered about the actual numbers. So what you can do is you can substitute the adjacent in for 1, and this will give us our, imagine 1 is our total weight, and our load factor will give us a 1 point something, which will be the increase in weight, or maybe 2 point something or 3 point something, but it will give us the amount that we need to increase. You then use this load factor to find our change in stall speed by using this formula here. It's very simple. It's basically the stall speed in the maneuver will increase according to the stall speed out of the maneuver times by the square root of this load factor. Right, so that was quite a big class. So we'll just summarize and get the key points across. So stalling is caused by a loss of energy at the leading edge of the aerofoil. This means that the boundary layer separates, and we also have this increase in form drag. The only way to get out of a stall is to reduce our angle of attack. The larger the effective angle of attack, the sooner we stall. On the wing design side of things, as our aspect ratio goes up, it means our effective angle of attack goes up, and it means our stalling angle goes down. On a rectangle wing, the root stalls first, which is good because it means that we get buffet and our ailerons stay effective for longer. On an elliptical wing, it all stalls at the same time, which means a very minimal amount of buffet and the ailerons become ineffective quickly. On a tapered wing, we have the least amount of downwash in the middle, so the middle stalls first, but we get no buffet, but we do get some aileron use maintained. On a swept back tapered wing, it's the tips that stall first, which causes that forward moving center of pressure, and the shorter balance arms, which create the nose up moment and can lead to that runaway deep stall condition. To reduce the span-wise flow, which will keep energy in the boundary layer, we add in wingtip fences, which physically block the path, or vortilons, which create a vortex which physically blocks the path. Other things we can do is wash out the wing to artificially change the effective angle of attack, as well as change the camber of the wing to do a similar thing. Some other factors that influence our stalling speed is our wing loading or our weight. Basically, if we've got more weight, we need more lift. So if we can't change the coefficient of lift because the wing design is fixed, that means we have to fly faster. So our stalling speed increases. We also have this formula for weight. Vs new over Vs old equals the square root of weight new over weight old to find the proportion of increase. In terms of configuration, our flaps increase our CL max so we can fly slower. Our Vs speed, our stalling speed, reduces. Our ratio formula is Vs flaps over Vs clean equals square root of CL clean over CL max flaps. When talking about landing gear, we add in drag, which causes a nose down moment. To counteract it, we have to increase our downforce at the tail, and that means that our downforce at the tail gets added on to the weight that we've got to overcome with lift, and that means that if we don't change anything, we have to fly faster. So dropping the landing gear makes our stalling speed go up. In terms of thrust, the propeller accelerates air over the wing, which means it separates at a later point and our stalling angle is increased. And on a jet, we actually have an upward component of our thrust force, which takes away from the amount of lift that we need. And this means that our Vs speed can go down because our stalling angle of attack has increased. In terms of center of gravity, If we have a forward center of gravity, it makes our balance arm longer. If the balance arm is longer, it means that we've got to counteract it with more down force from the tail. And this additional down force is added on to the total weight of the aircraft that needs to be overcome by lift. The same sort of thing as is happening with landing gear. So a forward center of gravity increases the stalling speed. In terms of altitude, you just have a lower density of air, which means that you have to increase the speed to counteract it if you don't change anything on the design side. So higher altitude, higher stall speed. In terms of maneuvers, you have to counteract also that centrifugal force as well as the weight. So you have to fly at a faster speed if you don't change anything on the design side of things. The amount that you have to do it is done according to load factor, which is 1 over cosine theta. Theta is the angle of bank or the angle of pitch. And to find out the level that it increases, you use this formula. Stall speed in the turn is the normal stall speed times the square root of the load factor.